So today will be our really last lecture, and we will try to cover polarization entanglement and Bell's inequality in the test of local hidden variable theories. So this is a very fundamental topic and difficult, honestly, to understand. So I'll try my best to see if I can give a good presentation on the topic. All right, so we'll cover a few subtopics. The first one is EPR, paradox. Okay. The second is, let's see. Let's just go to Bell's test. Okay, or Bell's inequality, or CHSH inequality. Okay. And quit. Is inequality spelled as INEQUALITY? Okay, thank you. So let me start off by discussing a very fundamental issue. And it goes all the way back to Einstein. All right, so we know that Einstein, we know that Albert Einstein has won the Nobel Prize, right, for his contribution in photoelectric effect. And he's also the man who devised the theory of special relativity. But his most known work is general relativity, right? And that is a fundamental theory of gravitation that has lasting effects. And even now, it opens a new fields in astrophysics, where we can use gravitational wave to see how the interstellar bodies moves and their dynamics. Those who we used to in the past, we can only use optical telescope to make measurement or make observations of the interstellar dynamics. But this is, but such method is unsuitable for, say, black hole dynamics, because black hole does not emit light. Yeah. So now we have this brand new tool, gravitational wave detector. We can see how black hole collides and all kinds of dynamics that it has. So that's great. But let's go back to the beginning. So we have Einstein, who told us that gravity, the origin of gravity, is the bending of space-time by mass. So if we have a ball, and if we represent the space-time around it as a 2D fabric, then we see that this ball will bend this sheet of, this is not a great drawing, but you see it will locally bend the structure of space-time. And as a result, if you have something that is nearby, if it follows its geodesic trajectory in this curved space-time, therefore it gets moved towards this body which distort the space-time structure. Okay, so that's the basic. That's general relativity 101. Is the basic idea behind general relativity. Now, we all know that this theory is one of the greatest mystery in the history of physics. I think, in my opinion, is that why general relativity and quantum mechanics are not compatible. Yeah, and the reason is in this case is pretty obvious, because in quantum mechanics we say that one of the feature, the hallmark of quantum mechanics, I would say at the most basic level, is superposition. right? If you have a qubit and you have another qubit, and this is in the 0 state and that is in the 1 state, that's no big deal, right? That does not show any non-classicality in any measurements that you do, right? But if you have a superposition state, then you have effects that does not show in any classical phenomenon. Yeah. So I would say superposition represents quantum mechanics. So when we start to think about why general relativity is not compatible with quantum mechanics, which I think it will be useful to just think about an example. So say we have this particle, this same particle in the superposition, if we could, okay? So it's in the superposition like this. So say like this, yeah? Now, according to general relativity, mass distort the local space-time, right? So since they are separated for quite a far distance, the space-time here is distort, kind of independent of the space-time here, right? They are like too dim in the space-time structure. Now, when you place a particle, a test particle in the middle, now the question is, where does this particle gravitate to? Does it go this way? Or does it go this way? Or half-half? Or does this force this particle into a superposition as well? Okay? So I think this example helps me see. So this is general relativity. General relativity. And this is quantum mechanics. Okay, so I think this example helps me to see a fundamental reason why general relativity as a theory of gravity is incompatible with quantum mechanics. Okay, now, so what do? Obviously, this kind of things cannot happen. The non-local, okay, so this issue with superposition is non-locality or non-local distribution, right? So particle could be here, or particle could be here. That is very far from the distribution of this guy. So we see that non-locality, okay, is at the heart of this conflict between general relativity and quantum mechanics. Okay, now, so of course you can imagine that how Einstein is unhappy about this discrepancy, even at the theory level. So his belief is that nature behaves as classical physics. His belief is that nature is dictated by classical dynamics. Okay, so what really characterizes classical dynamics? There are two features that we can think about when we think about classical. The first feature is locality, or non-local. So whether it is, so in terms of locality, whether it's local or non-local, okay? And so we know that classical dynamics certainly side with local, right? What's the second feature about classical dynamics? It has all this measurement outcome prescribed to it. So every measurement or every particle you make a measurement of, either for a wave or a particle, doesn't matter. Your measurement outcome, before you do it, is already prescribed to this object for all time. Okay, it has been carried, this property, for all the time. It is definite. It is deterministic. You don't even for, say, gas particle, right? When we have a gas particle, yes, we have a lot of, fluctuation randomness, right? But when we look at each single particle, we know that when the heat starts, when you start to heat the gas, right? This particle is moving towards that direction, and this particle is moving toward this direction. Every one of them has a predetermined, through the physical process, they have a predetermined, they have a property that is determined by the physical process, and they carry that property with them for all time. Okay, so this is called a prescript. Is that a word? Like pre-assigned. Man, I hope I'm not making a new word. Okay, but this is what I mean. So it has a so if you measure a property, that property belongs to it. That property has what is carried by the object before your measurement already. So that property is objective. Okay. So this is called realism. Okay. And I guess the opposite is non-realism. Okay. Or we could say deterministic. Okay. So so independent of measurement. Independent of measurement. Okay. Like this is the key. So the property of a particle that shows in the was there already, is independent of the measurement. Whether you measure or not, it doesn't matter. Okay. So that's realism, and the other is, of course, I would just call it non-realistic. Okay, realistic. Oh no, sorry. This is called real. People just call it real, and this is probably just non-real. I wouldn't say surreal. That's like another idea. But real and not real. Okay, and not local. And local. All right, so we see clearly that if we just use this property, we could kind of just group all classical theories possible here. Yep. How about quantum mechanics? I mean, this is, like just binary. So if all the theories have these two features, these two binary features, then this categories, one of them has to be classical mechanics, classical physics, and the other has to be quantum physics, right? Yeah, correct. Quantum physics. Okay. Not real. And why is that? Why is it not real? Because this collapse mechanism, associate with measurement. Right? If you do not do the measurement, you do not collapse the wave function. So the wave function is a superposition state. When you do the measurement, you collapse the wave function. The wave function is now a basis state. So the state has changed. Okay, just the mere act of measurement changed the state. So collapse associated with measurement. and this kind of association can be manifested in many different ways. But right now, let's just say that the collapse of a superposition state is sufficient to say it is like not real. Okay. Okay. So real is independent measurement. Okay. Cool. Now, so we all have heard of this this infamous 3-letter acronym EPR, right? You know what these names are? Huh? So this is Einstein, Podolsky. How do you spell that? Yeah, this it's difficult name to spell. I need to I need I need to look at my cheat sheet too. Okay. Give me a second. Podolsky, and this is Rosen. Okay. The full name is Boris Podolsky, and this is Nathan Rosen, and this is of course Albert Einstein. Yeah. So 3 authors. Although this is a leading author, but actually this paper, the PDR paradox, is mainly Podolsky's idea. Okay. All right. So anyway, in order to in the beginning of quantum mechanics, there was like a lot of debate about what it is and how is it different from classical physics, right? So it is Einstein's belief that the unified theory must root for classical physics, must has its root in classical physics. So it must be in this category. Okay, so right now, classical physics as we know is Newtonian mechanics, and maybe it's incomplete, maybe you still need more development, maybe there are some element missing. So in Einstein's mind, he imagined that if someday we can find this unified theory, it must be of the same nature as classical physics. Okay, and if it has, and why must it has the same nature as classical physics? Because he personally believes that nature is local. Okay, nature is local, and local means okay, maybe I should explain a little bit of what local means. So sure, this thing that has a distribution that's non-local is non-local, but local really means that what happened in one place does not get to affect what happened in another place that has a space-like distance. Okay, so it has to do with causality. Causality does not exist between there's not event between two events that are separated with space-like space-time distance. Okay, this space-time distance. Okay, we kind of we all know what the space-like distance means, so I won't explain it. But so that's what local means. Like what happens here. What happens in Taiwan doesn't affect anything in India. What happens in India doesn't affect anything in Taiwan at this very moment. Okay. And so Einstein's core belief that the ultimate theory must fall into this category, local real. All right. So they devise an argument to illustrate this point. Okay, and sort of not just for illustration, it's more like a proof that nature must be local and real. Okay, and what is that? What is that thought experiment? Let me describe it in modern languages. So we know that particles, a quantum particle, if this is a quantum particle, so you see he's using quantum mechanical language to describe a scenario where a paradox is result, a contradiction result. So this is a quantum particle. Okay? Particle. Gosh, what happened to my spelling? Okay, we know quantum particles is not really a particle, it is a wave, right? Or at best, it is a wave packet. That's what a quantum particle looks like. It's always a wave packet, right? Before you collapse it, it's always a wave packet. And this wave packet has a width in space, and it also has a width in momentum, right? Okay, cool. Now, that's all good. But what if, so and these two are conjugated variables. So if one has a broad distribution, has a broad width, and the other will have a narrow width. Now, what happens if we have two identical particles, okay, that both are quantum, so one is this, and the other is this, like they are identical, except maybe this only difference is that this is centered at positive momentum, and this is centered at negative momentum. That's all. Okay, and this construction is just so that we can measure them independently. All right. Now, so Einstein argued that sure, if you have both particle A like this, particle B like this, that's no problem. You can describe it with a quantum state like this. Let me see. This is particle A. This, or system A. This is system B. And let's see. What's the best way? Okay, maybe this. Okay? All right, that's fine. So Einstein said this is fine.
Why only momentum?
Huh?
Why only momentum?
Because these are conjugated variables. Okay, so there cannot be both so they cannot both be quantum numbers. So you either choose to work with one base or you work with the other base. All right, so we use one of them. Okay. Now, so he said this is fine. Okay, but what happened if, since this is a two particle state, right? What happened if we have a scenario where, somehow they are entangled? Okay, so what does entangle mean? Entangle means there exist, that their behavior are coordinated. So if one goes this way, the other will go that way. If one is up, the other will be down, something like that. Okay. So he's saying, okay, what if they are entangled? Okay, and the other state is described by in the basis of position. Okay. So let me put it in a more intuitive way. So this is what I mean by entangled. If one is here, okay, the other will be here. Yeah. And if one is here, the other will be here. So this is like the front of the pulse. Sorry, this is the back of the pulse, and this is the front of the pulse. Okay. So say somehow they through some kind of arrangement, I don't know how, but they can be. There is a correlation that is introduced to the system, so that now they can be in this. Let me just call this Ka or Pa, okay? And let me call this Pb, and let me call this Xa. Let me call this Xb. Yep. So by Pb, Pa, X, well, I mean the state that is centered at this location, at this value, the state that it still has a width, but the width is relatively small compared to this wave packet. Okay. So say they are entangled. So we have a new state, and the new state looks like this: Pa for particle A. Sorry, let me just use 1 and 2 to avoid confusion. So let me just use 1 and 2. So Pb. So this is similar to this. It's similar to this, right? But now, say we have this in a superposition state, and the other state is described by in the X spaces. That's not illegal, right? This state could be expressed in the P basis. So you have like a sum of that. Yep. But if you transform it by Fourier transformation, then it will collapse into this wave packet. Okay, so that's allowed. That's no big deal. Okay, so two kind of position, two kinds of momentum superposition. Okay, but with this more complex momentum superposition expressed in the X spaces. Okay, you can imagine that if you have this state, you do a Fourier transform, what do you see? A single slit diffraction pattern. Okay, so, and that is like distributed, have many peaks. Okay, so that's no big deal. So that is allowed. Okay, so he said, all right, so this is legal with quantum mechanics. This is also legal with quantum mechanics, right? And what's the component? What is the gradient here? Voila, superpositions, right? Now, and why does he want to invoke superposition? Because superposition has to do with real and non-real, right? And why does he want to do? Actually, it is perfectly okay if we just put this particle center at 0. It's perfectly okay if we just do that. Okay, and we could just put this as PA, a positive state, and This is PB. Okay, that this is also fine. Okay, so he's saying, all right, so we have this ingredient of realism or not real, non-real, and that's now propagate the system, without the system evolve. Now, since PA is sitting at the positive side of the is positive momentum, PB is a negative momentum, that these two particles preparing this state will separate. Okay, so that's wait until they separate far enough. So this goes like here, and this goes like here. Right? So they are very far away. How far? Well, I don't know. Maybe as far as the city. Okay? So that's pretty far, the city, the span of the city. Okay, so this would be like North Hsinchu, and this will be like South Hsinchu. Okay. Now, he's saying, okay, imagine now we have done two measurements. One measurement is done here, and we have here a momentum analyzer. Okay, I can it's like I can use a drip tube of something to measure its exact momentum. Okay, now here I want to use a screen, like a maybe like a camera. Okay, I want to film this particle. I want to like shoot photons to it and then collect the reflected photon and then like see where it is. Okay, so I have a camera. Okay, and this is a moment, this is a position locator. Yeah? Okay, so now for particle 1, what does this result give me? So regardless of the state, what does this two measurement give me? This measurement gives me that particle A, this measurement gives me that particle A has the position that is a little bit behind the center of mass of the wave packet. So if I measure it many times, I see that, right? So this gives me the particle A position. Okay? Or I can just time it. I know, like there's a way for me to just pin down the position as it is described here. Pin down the position value. Okay? In the meantime, here, the measurement gives me particle a result of particle B, particle 2, okay, PB, okay. That's no big deal. Well, but the big deal is if quantum mechanics is real, if quantum mechanics is valid, then this state must imply that this result gives me, because one, I know they are in superposition, but I don't know which particle is in PA and which particle is in PB, right? But if this give me PB, then particle 1 must be in PA, because I have them here. I collapsed the wave function, right? Now, yeah, although I have many positions, momentum state here, those are different eigenstates. They are orthogonal to this eigenstate. So if I measure this, I basically collapse everything to this product state, and then that will imply particle A1 has PA. So through this, you see, we can arrange we can arrange a type of measurement, a measurement scheme that measured both XA and PB with arbitrary precision. Okay? So why is that awkward? Because remember, quantum mechanics told us that the state of a quantum particle gets collapsed by the measurement. Okay? And so when you make a measurement of one property, then it's conjugated. Then you collapse this one, then its conjugated variable or property will have like infinite width. Yeah, so because this is the uncertainty principle working in terms of the measurement theory, in the context of measurement. Uncertainty principle working in the context of measurement theory. Right? So quantum mechanics that forbid us to measure in one measurement both X and P with certainty. But you see, in this arrangement, we get to measure this and we get to measure this at the same time. When we measure this does not suddenly make the P momentum goes to infinitely wide, right? Because here the quantum mechanics force it to collapse to also the other state. So we can use in quantum mechanics to defeat uncertainty principle. You see, that's the paradox here. That's the paradox they try to construct here.
How do we measure PA? You only measure PB, right?
Sorry?
You can only measure PB here.
Right? Yes.
But you cannot measure PA there. You measure PA the other place.
You don't, because through entanglement.
We know, but we are not measuring.
No, entanglement apply that. Yeah? Entanglement apply.
Because in the location 2, there is no PA. So we can measure PA in the location 1. Right?
No, that's not what quantum mechanics say. Quantum mechanics say.
No, we can, if we measure at location 1.
This is implied. This is not measurement.
Okay, yeah.
This is implied.
Yeah.
Implied by the entanglement.
Yeah.
Okay.
So we can assume that's.
Yeah. Because quantum mechanics, like we agree.
Yes.
When we start, before we start this experiment, we agree that we can somehow prepare in an entangled state. And the entangled state looks like this. And I told you that this part could be expanded in terms of the momentum basis. You have like many peaks, right? And let's assume that these peaks are now overlapped with PA. Okay, so PA is orthogonal with these peaks. Now, when you make a measurement and you collapse the wave function, right? Out of all this superpositioned product state, you collapse to this state. Okay, so this guy. If this is PB, then this is PA. Particle 1 must be in PA, right? In the meantime, we can measure the location of the other particle. So we inquire its momentum information through the measurement of the other particle, and we inquire its position information with this particle. Okay. So through one measurement, now 2, but through one measurement, but 2 particle, by the merit of entanglement, we can defeat uncertainty principle. Okay, so that is the paradox here, because uncertainty principle is quantum mechanical, and the entanglement is quantum mechanical. So it's like showing, oh, uncertain principle and entanglement are incompatible. All right. And thus, quantum mechanics is flawed. That is the main claim of this paper. Okay. Yeah. Now, let's take this closely. When we are laying out our measurement scheme, we say that, oh, we do this, but we can also do this, right? This is the classical way of thinking. This is like, we are like implicitly we are applying our this real property here. We're saying that, okay, the momentum state and the momentum state of this and the position state of this, the momentum state and position state are prescribed to the particle at the moment when they separate. So she just carried this information with it to the detector, right? And here we choose to measure this, okay, leaving PA unrevealed. But the other measurement tell us what PA is, okay? So the other measurement reveal the information of PA. So thus, it must have both XA and PA to start with before the measurement. That is a theory. That's like a real theory, deterministic way of thinking. Quantum mechanics is not like that. Quantum mechanics is not real. So he says collapse is associated with measurement. So the moment you measure this, right, you collapse this to a momentum state like this. That means this also get collapsed. Okay, and if it get collapsed, you cannot measure XA, right? Because XA is basically a sum of momentum states. So if you collapse to this one, then you're not in this superposition of this bunch of momentum state. So you are not able to measure XA. It's just not possible to do that because of this collapse mechanism. Okay, so this is, you see, so this is saying that it's the XA and PA, quantum mechanics says that these properties are not carried with one. It was in an undetermined state until you collapse the wave function, and then when you collapse the wave function, everything fall into the basis state, and then the measurement is according to that. Okay, you see that? And also there's this issue with local and non-local, right? So local means causality does not exist between two events. So that means when they separate far enough, when I measure this, it shouldn't affect the state here. So even I collapse particle here, I will not collapse particle here. Okay? But quantum mechanics say no. I allow non-local. I'm a non-local theory. So when you collapse, however far they are separated, even one is in the moon and the other is on Earth, when you collapse this function, the other gets collapsed at the same instant. Okay, so you see how this paradox is really embedded. This paradox about quantum mechanics is really embedded in this context of local realism. If you think about quantum mechanics in local realism, yes, you have this paradox. But if you think of quantum mechanics in non-local and non-real, you're no problem, okay? So what do we gotta get out of this? So what they propose is there must be, so in order to preserve this property, to make quantum mechanics work to resolve the paradox and make quantum mechanics work as a local real theory, there must be some kind of hidden knot. There must be some kind of hidden physical entity that we have failed to discover. Maybe it's in the vacuum field, maybe it's in the genie, maybe it's this and that, okay? So maybe there's something that is physical, that is local and real, and that controls how the randomness come out. Like that is like everything. It makes everything local and realistic, but we just haven't measured it. So our the paradox exists. If we discover such a hidden variable, then the paradox can be resolved, and quantum mechanics can be used with this addition of this hidden variable. Quantum mechanics can be local and real, and that will be our ultimate theory. That is the whole deal of EPR paradox. Okay. So this whole thing, it really is about what does the ultimate physics theory look like. Okay. So it's not just a boring paper where people just fight for nothing. This is a serious paper, and they try to find out what does the ultimate theory look like. For now, it seems like quantum mechanics and classical physics are in two different camps. This paradox, this paper suggests quantum mechanics 2.0, okay, with this hidden variable could make it work here. Okay, so this is like quantum mechanics 1.0, and this is quantum mechanics 2.0. Okay, with hidden variable, with hidden variable.
How it will still be non-deterministic, right?
It will still be non-deterministic only if you do not know. So so basically, what the hidden variable is that it will carry all the non-local and the non-real into it. So all this strange property are there because this complete information of this hidden mechanism is not revealed to us. The mechanism by itself is local and real, but when its information is not revealed to us, we see as if this whole thing is non-local and not real. Okay, that's the idea here. So with this implementation, with this supplement, we can fix quantum mechanics and make it work with local and real, just like other classical theories, and it will work with general relativity. That's the whole thinking behind this. So this is a rather subtle point, and to this whole discussion is quite philosophical, and to make real use of it in experimental setting is difficult. Yeah. All this discussion is rather qualitative, right? How do we really know if the ultimate theory falls in this category or this category? We don't know. Or maybe they are here. Like, what the heck, right? So this really, so this paper, well, it sparks a series of discussion in the physics community. It is not of practical use to the experimentalist until John Bell come along. drum bell. All right, so we will take a short break now, and then we'll move on to the drum bell test. Okay. All this discussion about Bell theorems and the CHSH inequalities are very abstract and mathematical, very difficult to follow. It will really help if we have a setup, a physical setup that explains what is what. And of course, the theorem is general, so it applies to all experiments. Not just limited to this one. Okay. However, using this optical setup, so using this optical scheme will make the discussion easier. Okay, so I'm going to just follow this, and this is also in the menu, figure 226. All right. So here we go. So we first start with an entangled state. Okay, and this entangled state is pretty straightforward, just horizontal. So let's use X for now to represent horizontal, and Y represent vertical. Instead of H and V, let's use X and Y just to be consistent with the menu. So X and Y are the polarization state of two photons. Okay, now they are in entanglement. That means sure. I wonder if I need to explain what is entanglement. All right, I think I need to, before I move on, I want to spend a little time and explain what is entanglement. Okay. Entanglement is a multi-particle state. It's a multi-particle state that is not a product state. Okay. All right. Okay, let me just try to give a definition of entanglement. Okay. Multi-party, right? Is that a word? Multi-party? Yeah. Not a product state. Okay. So what does it mean by multi-party state? Sure, it could be two particles, 1 and 2, right? So phi 1, phi 2. Yeah, this could be two separate particles, or it could be 2 degrees of freedom of one particle. Okay. It involves, basically, this is one physical system and this is the other physical system. And when we talk, the minimum definition of a physical system could just be different degree of freedom. Okay. And of course, you can also use different particle, same degree of freedom, but different particle to construct this multi-party state. Okay. So anyway, but it involves two physical systems. Involve two or more physical systems. Now, this is called a product state. So because this is just a pure state of system 1 and this is a pure state of system 2, and we do a tensor product of it. So that's a product state. Okay? So we have state 1 of this multi-party state. We have another multi-party state that looks like this. Okay, so you see the first system is in the pure state, in the eigenstate, and the second system is also in the pure state, but it's now in the superposition state, right? This still is a product state because it is system 1 tensor product with system 2. Okay, so you can write this as system 1, and this is, I don't know, beta system 2, right? So you can always write this in the tensor as a tensor product of pure state of the two systems. All right, so these are the multi-party state, and these are not entanglement state. This is just product state. Entanglement state is something like this. Maybe let me just use A and B. Let me just use A and B. A, B. Okay. A, B, B, A. Okay, this is the entangled state. We cannot make this into this form. Just cannot.
But it's not only that, we can also have AA plus BB, right? Doesn't necessarily be opposite. Like we can have AA.
Of course, of course. The point, of course, you're saying, of course, we could have A plus B. Okay, it doesn't matter what is the state that each particle, each system take. The point is they just cannot be factorized into a product state like this. That's the whole point. So if you have a multi-party system, okay, and there is in the state that's in the superposition state, that cannot be factorized. So this is necessarily involves superposition. And if both particles are in the both in superposition, okay, if both are in superposition, and they cannot be apart. Okay, maybe I should say both in superposition. If they are both in superposition and they cannot be factorized into a product state, then that's entangled state. I could have A, B, and A, sorry, B. Yeah? So you see both particles are in superposition state. Okay, so that agrees with criteria 2. Both particles are in superposition state. But now they could be factorized into they can be factorized into a product state. So this is not an entangled state. Understand? Okay. So understanding this criteria about entangled state is important because kind of give you a guideline on how to produce an entanglement, how to produce an entangled state. Yeah? All right. So when in atomic physics, especially cavity QED physics, there are a lot of examples where you use you start with a superposition state in both systems, and then you use some kind of collapse mechanism to collapse this state into an entangled state. Okay, so this is a good guideline for as a recipe of how to regarding how to make entangled state. Okay, you have a question, Phoenix?
No, it's just last time I just want to mention about the that moment. Last time when you mentioned about this, when you mentioned about the entanglement, actually, I mean, for the side two.
Yeah.
We are not sure it can be written as the.
Oh, like this?
Yes, we need to check.
Why? This whole thing is beta 2. This whole thing, this is particle 2. If one is in the eigenstate and the other is in the superposition, right? That this superposition itself is a state of system 2 only, so that naturally is.
Particle 1 will not give us which state particle 2 is in.
Yeah. Okay. So anyway, I'm trying to give a lot of examples to tell you what is not an entangled state. Instead of giving you a prescription of what is entangled state, I tell you what is not an entangled state. Okay. All right. So that is just and why is entangled state interesting? Why are we like when we try to do when we try to search for the ultimate theory of physics, like the quantum mechanics 2.0, why do we want to use entangled state? Because entangled state is really the next level of non-classicality. You have seen superpositions in classical physics, okay? That is not a new concept, right? You just haven't seen wave-particle duality in classical physics, but you have seen superposition, the concept of superposition in classical mechanics, right? Water wave, right? Light wave. Even coupled oscillator, right? You can have coupled oscillator. You can have a coupled oscillator coexist in many eigenmodes. That is a superposition, right? So there's no problem to demonstrate the concept of superposition in the context of classical physics. You cannot demonstrate wave-particle duality, okay? But you can demonstrate the concept of superposition, and that is really a source of misunderstanding for some people, because whenever they see a superposition, they say this is quantum mechanics, yeah, right? And they will think light diffracted or going through double slit or a grating, that is a quantum phenomenon. Not true. Superposition, the concept of superposition exists in classical physics. Coupled oscillator, light wave, acoustic wave, water wave, name it. Okay, I can have wave system, I can have particle system, I can have them all, and they can all have superposition. But entanglement, well, that is just, you just cannot, that's just like a brand new concept, brand new physics concept, right? You just don't see this kind of thing or anything like it in the realm of classical physics. Yeah. So entanglement and superposition are really like the hallmarks of quantum mechanics. When you want to check if something is quantum mechanical, you check for this two property. But entanglement among these properties is like the smoking gun. Like this is irreplaceable. You just cannot find any classical system that would do this, that would even demonstrate such concept. Okay, so what I'm trying to say is like the most quantum mechanical thing in the world is entangled state. That's like another level of non-classicality. Okay, so when we try to figure out if the ultimate version of quantum mechanics could be local and real, right? We of course want to use this, the biggest target, the biggest target to tackle, which is the entangled state, and we use it, and we see if this can fit. Okay, that's why Bell's test is arranged with an entangled state instead of a product state, or just a superposition state, entangled state. The entanglement, the element of entanglement is introduced so that this could be the ultimate test of quantum mechanics. Okay. All right. So let's try to construct an optical skin for Bell test. All right, so this might be this part of the lecture might be a little slow. If you want to take a nap, that's fine. But you might not be able to follow it after you wake up. All right, so say we have a source, some kind of entangled light source. Later we'll explain how do we make such a source in our experiment. But right now, let's just suppose we have two photons.
We have seen in the previous classes to create entangled sources.
No.
It's through BBO.
Oh yeah. But no.
One of the examples.
But not actually no. Do we? They are entangled. Yeah, they are entangled in momentum. Okay, they are entangled in momentum, but not polarization. Okay. So right now, let's consider this system with.
Since they have the ray coming through BBO, will have same polarization, right?
Yeah.
So they are entangling polarization.
No. if they are in the same state in the polarization, they are product state. In terms of polarization.
It's like if you put horizontal polarization, you get horizontal. Both will be in horizontal polarization. Vertical polarization, both will be in vertical.
No. Just don't get yourself confused. Let's focus on this. Let's focus on this. Okay. So say we are able to produce a photon pair, and the photon pair has two polarization, one horizontal, one vertical. Okay. So we use X to represent the horizontal, Y to represent the vertical. Yeah. And particle one goes here, particle two goes here. Photon one goes here, and photon two goes there. And here we're really talking about like single photons. Yeah, single photons. Now, the state that we have is written as this, like we write here. So this is in the superposition. This is in the superposition of this and this. Vertical, horizontal, and vertical. Okay? It's in the superposition of this and that. And the other one is also in the superposition. But these two superpositions are not like this. They're not separated. They are entangled. That means the other guy is this. Okay? Okay, so the other guy is also in the superposition. Now, we have an analyzer. We have an analyzer here, which I will show as a cube. Okay? And this is a biorefringent cube. And what this does is it will pass one, it will pass one polarization and will deflect the orthogonal polarization. Okay? So deflect the orthogonal polarization. And what is, and how is this defined? It is defined through some kind of optical axis. Okay, it is defined with some kind of optical axis in it. Okay, which we will denote with. So let me just draw it like this. Which we will denote with an angle with respect to x. Okay, so if this optical axis or this kind of or some kind of axis in the crystal is at an angle of alpha with respect to the horizontal, then it will pass the let me see. It will that's no problem. You'll pass the rate that has the polarization in alignment with this axis. So this is not an optical axis. This is an axis that I define with respect to the optical axis. All right, so this is some kind of axis, and by the way, this can be physically constructed. So I'm not just making things up. Okay, I just don't want to go into detail. Later, when we talk about optical implementation, I can go into detail. But here we just agree that there is some axis in the crystal where if you have the polarization aligned with this axis, it just pass through. And if you have polarization orthogonal to this axis, it will deflect. Okay. Now, we put the stand analyzer. So basically, so analyzer is a crystal plus detector. Okay, so we have a box and the crystal is in the front, and we have two tiny detectors in the back, and depending on it's passing through or deflected, we can detect it. Yeah. Okay, so this is also the same deal. We have this other cube here, and it also has an axis like this, and it is beta. It is making an angle with the horizontal. The angle is beta. And again, if the polarization agree, with the axis with this axis, it pass through. If the polarization is orthogonal to this axis, it gets deflected. So like this. Okay, so these are our two analyzers. Okay, so this is the setup of our experiment. Now the question is we want to ask is, so we assign that if we pass through, we assign a value, a detection value called +1. Okay, we just register as +1, and this we register as -1. So we can connect this to an inverter, right? So a positive click will get inverted to a negative signal, and that will give us a -1. And we put a threshold to distinguish whether this is +1 or minus. Yeah. So this can totally be done, no problem. +1, -1. Yeah. Okay. Now the question for us is, what is the expectation value of our measurement? The expectation value of our measurement according to this state. What is that? Well,
so is it like, do we get for the same state +1? Like we get x in 1 +1.
So say if this is horizontal,
okay,
right? Then
yeah, in both horizontal is +1, right?
Right.
Okay.
But if this has an angle, that's a different.
Yeah.
Okay. +1 and -1 are defined with respect to the analyzer axis. Okay.
Yeah, I want to write.
And the analyzer axis can be oriented either horizontally, vertically, or anything in between. That's no problem.
No,
okay.
I was just between the two detector. Does it it sees the same state as +1, right? That's what I got.
It sees the same state as +1.
Yeah, means if
no. This could be, for example, this could be 90 degree, and 90 degree will correspond. So if you have this guy, right, in y.
So, for example, we have like x and y state in horizontal, vertical.
Okay. If we just have this, right?
Okay, yeah. Mm-hmm. In the first crystal, if I get x, I get +1. Y, I get -1.
No. Depending on your setting on alpha. So if you set your alpha as vertical,
yes.
Then you get +1. Then you get +1. If you set your alpha as horizontal, then you get -1. Because what comes here is the vertical polarization, right? What comes here is the vertical polarization. So depending on your alpha, if your alpha is this, right, then this will get diffracted, and that will be a -1. If your alpha is like this, then this will just pass through, and that will be a +1.
What I want to ask is that we take alpha and beta differently. So
yeah,
it's
we
not
can.
Like we take itself.
No. Yeah, they can be set at independent settings. Okay.
So the expectation value depends upon alpha.
Yes. Correct. So that's, since we have 4 different eigenbases, right? So it's the probability is really how much probability we have to project our state into be alignment with alpha. Okay, so we have basically 4 possibilities. Okay, so you can be aligned with the alpha, and at the same time align with beta. That is your state. That's state possibility 1, right? If that's the case, you get +1 here, +1 here. So you have +1 times +1. So that's +1. Okay, so the expectation value of this joint measurement. I mean, this is a joint measurement that we're talking about because we have a 2-particle state. Okay.
Why is +1 times plus?
Because this gives me a click. This is a joint measurement. I want to know.
Yeah, but
the expectation
there and +1 here, so it should be +2, right?
No. Here the rule is that I have my my measurement result as a product of my individual measurement. Okay, so this is a joint measurement, and I define the joint measurement result is the product of these two. Okay, so if this is called S, if this is called S, and this is called T. Okay, I want to know what is ST, S times T. I want to know what is S times T, this specific observable. Yeah? Okay, maybe I should write it like this. Expectation of this is defined as dot T average over. Yeah? So an ensemble measurement of this state. Okay, I prepared this state many times, prepare in the same way, and I do the measurement. And I do it many times. Okay? Sometimes I will have this state collapse to alpha and beta. Yeah? Sometimes I will have the state collapse to alpha and beta vertical. So this looks like this. I'm sorry. Yeah, and in this case, I will have +1 times -1. So this is -1. Maybe I should just write. I should just write it here. +1 times 1. 1 times 1. Okay, and this is 1 times -1. Yeah. Okay. So these are this basically are projections. Okay, projection to 2 eigenstate, and these are the eigenvalue for that eigenstate, right? So this, yeah, okay. So this can be seen as the eigenvalue. Okay, and this can be seen as the eigenstate. Yep. Okay, so now the gain is, yeah. So you know how to play this game. Okay, in this case we have -1 and +1, and yeah. Yep. Okay. All right. So great. First equation down. All right. Now, what do we? If we will have alpha and beta just on the vertical, set at vertical or horizontal, then we can also directly calculate this, right? Because this is horizontal and this is vertical. So we can just calculate this, and then we will have the answer. We have the expectation value. Yeah. And yeah, why don't we do that for just one example, and then we will try to proceed with the general case. Okay, I think that's how we like it, right? So say we have alpha equal to 0 and beta equal to 0. That's like the simplest setting, right? Now if we have alpha equal to 0, beta equal to 0, then again this will be 0, right? This will be 0. Because this is basically essentially xx, and we have xy or yx. So the inner product of xx and xy or yx is just 0. Okay. Now here we have 0, so we have basically x and y, right? So we have x and y, and that will be this guy. So that will be this guy square. Okay, now we have y and x, right? Y and x, we have this guy. So that will give us square 1 over square 2x. Yeah, and here we have again 0, because this is y. So this is 0. Okay, so this is pretty easy. Yeah. So what does this give us? This gives us a minus 1. Yeah? Okay, cool. No big deal. And we can play this game for 90 degree, 0. Okay, so this is pretty straightforward. Okay, but what if it is an angle in between? Okay, that is harder. Okay, and to do that, we have to use this projection thing. So 5. Okay, so basically, I mean, this is pretty straightforward, because if we have the alpha vector like this, it is the axis is this is basically a vector, right? A vector that has an angle with respect to the horizontal. Then in terms of the vector, you just write it like this. This is basically alpha vector is cosine A x unit vector and sine alpha unit vector, right? Yeah, and this is, of course, just so just in case this is not obvious to you. So this is the alpha vector, and this is the alpha plus pi over 2 vector, right? So you can see that the x component is now minus sine, and the y component is just cosine. Yeah? And the same with beta plus pi over 2, right? Okay, so let's work this out. Let's work this out. We have 4 bases. Yeah? So how does this work? Let's see. Let's just do 1. Let's just do 1 and see how this goes. So this is cosine x and psi y. So this is the analyzer on the right. Okay, so let me just label this. This is the analyzer on the right, and this is the analyzer on the left. Okay, so this is on the right. Oh, sorry. This should be bra. And this is cat. This is also bra, sorry. This is analyzed on the right. Okay? And we have this guy. Yeah? It's no problem, right? So this is basically alpha, beta, and that. So I'm just, there's nothing novel about this. Just rewriting things in different symbols. Beta. Okay. Right. That's, we can expand this. So this is cosine, cosine, and this is x. Yeah? Cosine, sine, this is xy. Yeah? So let me label this a little bit. So this is L, sorry, this is right, and this is L. This is right, this is L. And we have sine A, cosine beta, y, x, sine A, sine beta, y, y. Okay. Yep. Okay. Right? So what does this give us?
0.
This is 0. So we have cosine alpha, cosine beta times 0. Yeah? And we have cosine alpha, sine beta times over 2, right? We have sine beta, cosine beta times 1 over square root of 2. And this is sine times 0. Okay? Great. So now we have here cosine alpha, sine beta. Yeah. All right. So let me just work with this. Sine alpha, sine beta. Right? And this, what is this? This is cosine alpha minus beta. Okay? All right. Now, with this very nicely written apparatus, it is very easy to, when you switch this to, for example, when we just switch this to this state, right? We know that this gets changed to minus sine and cosine, right? And this gets changed too. We have also like a minus sign deduced, right? So this is gonna change, right? And if we don't for example, if we don't have a Bell state like this, okay, there are 4 Bell states: xy, xy plus yxy, xy plus yx, xy minus yx, xx plus yy, y xx minus yy. Right? So there are 4 Bell states. So the 4 Bell states will have different, projections. So they will change the value here, also the sign here. So this result really depends on which Bell state you use, right? But for now, let's stick with this Bell state that we use. And for alpha beta, we give the result of this. And let me write down result for the other ones. And okay. Let me write in this order. Sorry, let me write it in this order. Okay. Yeah. Okay. I wonder if maybe it's a minus sign here. Let's see. If I have, let's see if we have a minus sign here. So if I have this as that, then this is minus, and this is cosine. Minus sign, and this is cosine. Yeah? Minus sign here. That's 0. Cosine here. Okay? And minus sign here, and cosine here. Okay, so there's no 0. All right, that's checked. Okay. I think. Wait a second. If I have minus sign, and this is minus sign. This is minus. This is cosine. Wait a second. This is cosine, and this is minus. Oh, so there's a minus. There's a minus. Okay. I think so. All right. You can check. But
I think both. There's no minus sign in the second one, right?
There's no minus sign here.
No, in the second one.
This one? I think there is. Let's see. We have minus sine alpha and cosine here. So there's a minus here. There's a minus here.
Else it'll be sine beta minus.
Here's a cosine. Here's a cosine, right? So we have a minus here. And that's a minus here, right? Okay.
Yeah.
Yeah.
It will be sine beta minus alpha in that case, so
Mhm.
beta like minus
Yep. All right. Good. Okay. So now we could calculate this thing using what we have, right? But if we have a different Bell state, this result is different. Yeah. So we have this guy, but it is squared, right? Plus 1, and we have this guy that is also squared. We have plus 1 and minus 1. We have the third guy. Minus 1, plus 1, the fourth guy. Minus, okay. Yeah. So what does that give us? Cosine minus sine, right? And this is cosine 2 times. Yep, 2 times alpha minus beta. Okay, so that is the expectation value. Okay? Okay, good. Now, all right, so these are pretty straightforward. No problem, right? These are just very elementary algebras. This is like quantum mechanics. No problem, right? Anybody? Okay, we'll move on to the hard part. Right, these are just very simple, basic quantum mechanics inner product stuff. There's no mystery about this. This is eigenvalue and this is eigenstate, and depending on which eigenstate you fall into, that is the eigenvalue you're gonna have. And if you have the eigenvalue here and the eigenvalue here, S, and the eigenvalue here, T, and you want to find out the expectation value of their product, right? Because the product will depend on the joint measurement. Right? You need to measure both to know the product, right? So this is the expectation value of the product, which depends on the joint measurement. Okay, joint measurement means both are measured. That's just it's kind of a silly word to use. All right, so these are like the 2 particle version of expectation value. Like we used to do this all the time with single particles, and this is the 2 particle version of that. There's no big mystery here. All right, so let me continue with the Bell stuff. Okay, so this is not Bell. This is just basic quantum mechanics. Okay. Oh, sorry. I'm sorry. I make a mistake. Very sorry. This Bell state that we're gonna use is not x y y y x. It is x x y y.
Then it makes sense.
My bad.
Yeah.
My bad. Thank you for spotting that. So, yeah. So this is sorry, I misread. The Bell state we're gonna use according to the menu is this. So therefore, let's just.
So first and last will be
Wait.
the other one will be 0.
Yeah.
And,
yeah. So this will be this guy, and this will be 0, 0, and this guy, and then we'll have 1. Okay, plus 1. Yeah, thank you. All right. Okay, now it comes to this Bell business. Okay. So do you know how random number is generated in a computer? Do you know how random numbers are generated in a computer? How do you know a series of numbers that you generate are really random? There's no correlation between all these members. Like if you generate like 1,000 numbers, how do you know they are really, if you plot them in the distribution, in the histogram, right? You're supposed to see a flat histogram, right? That will indicate a true randomness. If you have anything that is a little higher, that something is wrong. Okay?
Even if it's flat, it doesn't necessarily say it's true random, because if it repeats itself, the sequence repeats itself, it's not true random actually, but you'll get flat distribution.
Oh, sure. You're right.
That's why in computer we mostly say it's pseudo random. It's not original random.
Sure.
Yeah.
All right. But thank you.
Yeah. To check whether it's random or not.
But this business of randomness is non-trivial, yes. I would say. To generate a series of random numbers using deterministic computing method, that is really, I mean, that by itself is kind of a conflicting idea, right? You're using deterministic method to generate random outcome. That's why that's the word pseudo-random. But usually in the computer, it has an algorithm that generate a series that goes through like it's like shuffles, and then you shuffle many times. If you shuffle enough times, it becomes random enough with respect to the next round. Okay. Now, before you give the random number, your function needs to take into a seed. Okay? And that seed will give you a random number. So C1 going through this function will give you a random number. C2 give you a function going through this function, this algorithm will give you another random number. And the task is if S1 and S2 are different, then you need to really show that there is no correlation between these numbers that you generate, this series of numbers you generate. Okay? But you see, the point here is if you use the same seed, you definitely get the same number. Okay? Or some number that is close to it, some kind of correlation exists. Okay? So you need to use a seed that is different enough. If you use seed, like for example here 2, and you here use 2.000001, right? Maybe the random number that you generate there will still exist some kind of correlation between this and that. Okay? So the point is this deterministic nature really sticks with the whole process. When the seed is changed, yes, your outcome could be very different. Your outcome can look random with respect to the previous outcome, but if the seed is not changed enough, your outcome is similar to the previous one. The whole deal is deterministic, right? This is the spirit of hidden variable theory. Hidden variable theory is like a random number generator. This hidden variable usually represent as lambda, represent a series of number A, B, C, D, a series of parameters, okay, a set of parameters that is used as the seed of the system, okay? And if these are not revealed to you, then the outcome they produce, the outcome they produce will appear to be random to your eyes, okay? But if this is revealed to you and you just change this a tiny bit, the outcome will appear to be correlated with the previous one. Okay, so that's the whole deal of hidden variable theory. It is actually a pretty smart construction. Okay, so it's at its core it is deterministic. Okay, but all the randomness, all this uncertainty are attributed to this unrevealed set of hidden variables. Okay, so that's what John Bell starts with. So he is saying he assumes that there exists a theory where the where the measurements outcomes are determined. So you can do like a number of measurements, right? But if the C is the same, then the different measurement, the outcomes are gonna be correlated in some way. Yeah? Okay. So a version of John Bell's theorem, which is constructed by CHSH. So these are 4 persons. This is Claude. This is Horner. This is Schimmerling. And this is Holt. Oh man, I'm proud of myself. I can remember 4 names. I think this is spelled right. Claude. Yeah, okay, whatever. Doesn't matter. Can you check for me? Can you check for me? You have a computer. Just type CHSH. Just see if my spelling is right. So the Bell theorem is like a very general theorem, okay? But to embody this theorem into physical experiments, we need to really like give it closer. SER.
Yeah.
And the rest are correct, right? HOLT. Yeah, HOLT. This is Hornen and this is Schimmerling. Yeah? Okay, cool. Not too bad. 3 letters wrong with okay, but this is good. So this CHSH version of the Bell test is probably the most used one. Okay, so they construct a parameter which is a combination of different measurements. So they call it S. Okay, so this is just there's really no good, like there's no physical reason behind it. It is just a mathematical construction. So they take 4 different measurements. That means you set this, for one value, for example, you set this one value, okay? And you set this another value, just kind of random. Okay, they don't need to be orthogonal or anything. They are just kind of random. Okay, and you take combination of both. Okay, so like this. Okay, and this. Yeah, so you basically pick 2 settings. Okay, so these are your 2 measurements or 2 experiments, and then you make another 2 experiments out of from these settings. Okay, so if you have that, they say you take your expectation values for each measurement, and you put them in a linear. You have a linear combination, a linear sum, and this linear sum, by the way, this form also has to do with the Bell state that you use. When you use a different Bell state, this has a slightly different form in terms of signs. Okay, but for the Bell's data we use, this looks like alpha, beta, minus alpha, okay, it looks like this. Okay, when you use a different Bell state, for example, if you use this one,
Why is the third term doesn't have minus?
no good reason. Okay, no good reason, just mathematical construction, so that at the end you will have this kind of inequality. If you have this Bell state to start with, then you will have minus, you will have plus sign here, and you have minus sign here. Okay, according to this book. Okay, so they use different. This book and this menu use different Bell state. So I'm just saying this signs, the assignment of these signs they are designed to give you an equality that reflect that draw a boundary between the hidden variable theory and
What is S?
S is just this linear combination. Okay? Yep. And if you want, you can say this linear combination belongs to this Bell state. Okay?
It doesn't have a name or something?
No, just S parameter. Okay? Yeah. All right, so there's really no physical motivation behind it. They are just saying that if you take your measurement result for 4 experiments and you combine it in certain ways, then this parameter will help you distinguish, will give you these different values, will give you different prediction. The 2 different theories will, the hidden variable theory, the local real hidden variable theory will give you a different outcome, a very different, completely different outcome, no overlap. Will give you a completely different outcome than quantum mechanics if you use this combination. And you can try if you just alter this sign and see how the derivation will lead you. Okay? But they are just stick with me and you'll see it. All right. So they say assume combining this parameter. This parameter combining the 4 experimental outcome. Okay? Yep. Now, remember I told you that the seed determined what the system looked like, right? So if you have the same seed, but you just arrange your apparatus differently, right? There is gonna be some kind of correlation exist. Yeah. All right. So this is in some sense, this is in a sense measuring the leftover correlation. Yeah. All right. So let me just say that this is a function of your random seed. Okay, and I'm gonna give this as a subscript to all your measurement. So that means all the measurements, although your apparatus is configured differently, they are nevertheless share the same system that has a random seed. Okay? That has the same random seed.
Lambda is the seed.
Hmm?
Lambda is the seed.
Yes. Lambda is the seed. Okay? So suppose your seed is not changed. So everything is deterministic, local, whatever, right? And this seed fix every details of your physical system. Then your expectation value will be, there will be a subscript of your expectation value, okay? And however you range your apparatus and do different measurement configurations, it doesn't matter. You all share the same seed, okay? It's all done with the same deterministic system, okay? And this system is determined by this seed, okay? So there ought to be some kind of correlation exist in this Benjamin outcome, all right? And this linear combination minus plus plus is to help us reveal that correlation, okay? Sorry? Yeah, that's just a random choice. Like I said, it does not need to be. These are two independent choice of measurement configurations. I can make them 0, 0, 90, 90, or I can make them 0, 30, or 0, 30, and this is 45, and this is 45. It really doesn't matter. It's just an arbitrary choice of 4 numbers that determine your measurement setting, and then you use that 4 number to create another 2 experiments. Okay. So you have some kind of correlation exists between the measurement settings, and that correlation also is there is also an additional layer of correlation. If this quantum mechanics, this will be it, right? But if the nature work with has this hidden variable in it, there's another layer of correlation that is characterized by this shared lambda. Okay. All right. Good. So so great. Now, what we're gonna do is we're gonna do a little average. Okay. So say we have done this measurement for the whole day, okay? And somehow the hidden variable changes. Maybe because of the moon, maybe because of the sun, right? After a long time, maybe within a short time, it doesn't change, so we can manage to do the full measurement with the same hidden variable, okay? No problem, but maybe after a long time, it changes, okay? So, and maybe there is some kind of distribution, maybe Gaussian, I don't know, and maybe it has like a value that the Gaussian is centered to, and so maybe there's some kind of distribution, okay? Let me just use rho to indicate the distribution, okay? So rho is the distribution of lambda, and you can imagine rho is just a Gaussian distribution that will work, okay? And this is the average value. Okay, this is the average value that I will have, yeah? And And in this case, of course, I'm going to have each of this measurement averaged. Why do I want to do this?
So what does rho play in this formula?
Huh? Rho is the distribution of lambda. So this is basically saying.
No, my question is, I understand like you take this, but it is equivalent to that, right? You're integrating over all the lambda.
Right. Yeah.
So in the final result, there shouldn't be any lambda. But
No. I'm just saying this is average over lambda. Average over lambda. There's no lambda. Right. Correct. This just indicates averaging over lambda. That's all. Lambda is now removed from my. All right. I'm running out of notations. If you really want, okay, maybe I can change my notation to this. If you really want, okay. Okay, I am gonna just change it to this, just because Mosfer does not like my notation. Okay, you happy? All right. So lambda in the subscript means average. Lambda in the bracket means that it's part of the parameters that sets the value. Okay, good. All right, now why do I want to work with this quantity instead of this? Well, because this is really hard to control, right? I really don't know how I can measure this. Yeah, maybe maybe if this hidden variable doesn't change for a while, then yes, I can measure or finish my 4 measurements at the same time. But how do I know it's not changing or not? It's hidden, right? I couldn't have any idea of its current value. How do I know it's changing or not, right? So I couldn't. So to measure this is really difficult, yeah? But to measure it, but if we assume that this has like a finite distribution, so this just this lambda could change, but it will just change within this interval. And if we do the experiment enough times, we sample all the different possible numbers, right? Then it don't need to be done at the same time. This 4 measurement doesn't need to be done at the same time. This can be done by itself for a while, and then this is done for a while, and this is done for a while, and it's done for a while. Okay, so so that is, I think this is also is in alignment in the same spirit of with this ergodicity. Ergodic, I think it's called that. Do you know this word? Yeah. Okay. So there is like a deeper reason to want to work with this quantity. Okay. But I think it's sufficient to see this as being motivated by our experimental convenience, since it's really difficult to get everything measured with the same random variable seed. So we do it with different rounds, and we do it many times, and we'll still get the same result. I think this is also called central limit theorem. Have you heard of that? Central limit theorem. Yeah. Yeah. Anyway, this random variable business is very convoluted and complex. All right. Now, there is let's come back to our let's come back to our example. All right. Because I don't want so this is pretty abstract, right? So let's try to use this in our example. So earlier we have the expectation value written out for everyone, right? And that has a pretty simple form, right? That just equal to this alpha minus beta, correct? Now, if we have 4 different measurements,
Actually, that result come from another component.
huh?
I mean, that result is come from another swap between x and y.
X, Y, Y.
This is, I mean, that result we call the chain of rotation.
No. We change only rotate. We don't change the initial source.
No, because
All right.
It's always X, Y, Y we are producing. We are not changing what we are producing. We are only changing the detector orientation.
it's like you are, I mean.
Yeah. I know what you're talking about. Yes, she's right. She's right because remember we have a lot of cosines and sines here, and we have the inner product of
I
XX,
I mean, just
XY.
Just write I mean, that sequence down, and then we can, I mean, fastly get the final, right?
Alpha and beta are on the detector side.
Yes, that's the state.
Yeah, but we are producing the same state output.
Okay, let me.
We are not changing the state.
Yes, but because you remember the initial state is like horizontal and vertical,
Yes.
but eventually is the best state we use is horizontal and vertical.
Yes.
So there's slightly different between the.
Okay, let me just do this again. Cosine alpha. Let me just do this quickly. X, sorry. X.
As long as we don't change the initial state, this is okay. It's no problem.
I see what you're talking about. Okay.
Because I parked my bike in the wrong place. So I get a ticket.
Oh. Good for you. You have performed a measurement and you fall into an eigenstate. Ticket or no ticket? Right?
Yeah.
I think that's a very valuable lesson.
But actually, I guess I saw there's many people parked there.
Yeah.
That's why I
See, this is.
Everyone gets tickets, so
No, not necessarily. This is random. There's superposition in it.
No, but actually,
Your H measurement is different. You can collapse into ticket state or no ticket state.
No, but actually, it's improved.
So everyone get tickets or no one get tickets.
Oh, then that will be a highly entangled state. I think that's called the Newton state.
Yeah, in this there will really.
Aye.
Yeah.
Okay. I think I okay. I think what I did is I made a double mistake, so I get the answer correct. All right. So earlier, what I had is cosine alpha sine and sine alpha cosine, right? The middle one. And then I somehow say this is cosine square minus sine square, and then I was led to the conclusion this is cosine 2 times alpha minus sine, alpha minus beta. So I made a mistake. But I get the right.
Yeah, you will still get that because like out of the 4
what I have
no,
what I should have got earlier is cosine alpha sine beta sine alpha cosine beta, so I should get this. This is what I should get earlier.
So,
right? This is what I should get earlier. This is what I should get earlier from this 2 cross terms. Okay? So I made a mistake.
Yeah.
Okay, I somehow see it as cosine of yeah, anyway, somehow I see it wrong. So I made a mistake, and that mistake, because I was reading this book, so that mistake didn't result into a wrong answer because I was like reading this book. So I still get it right.
There is another problem in what you write. The last step is not right. It's sine alpha, sine beta. 4th step.
No, it's cosine, cosine,
sine beta.
Sine beta, yeah, you're right.
And beta in the last.
Yeah, and we all agree that this is cosine alpha minus beta. Right? Yes? Okay. So this is, so the reason I'm writing this is because I want to show you that I was following the answer given here. So even my calculation was wrong, the answer was still correct. Okay? So what is this? Oh, so this answer stands. So with the 4 different combinations, this answer stands. Okay? Because the book says so. Okay?
Yeah, because only thing that changed when you change alpha and beta, alpha to alpha plus pi by 2 is like we get the 4 results, but changing sign or from sine to cos.
Yeah.
So when you plus all of them, you get the same result.
It doesn't matter. It doesn't matter. Let's not waste time to discuss how a mistake result into a right answer. That's just a waste of time. Let's focus on this. Okay. So this is the right answer. Yeah. Okay. You can run the. We have the video. You can run the calculation again on your own, and you see this is the right answer because I was following the answer here, not my derivation. And let's do this. Okay, so let's calculate this. And what is this? This is cosine 2 alpha 2 beta, right? So this is pretty straightforward. Cosine, except this pen is all beat up. Okay, so maybe it's better if I just write this like this. Okay, so that's easier to see. So I'm gonna write this for both the quantum mechanical and, so this is like the general thing. This hidden variable and quantum mechanical thing is not here yet. Okay, I'm just constructing a parameter that is a combination, a linear combination of my measurement results. That's all. That's all I'm doing here. So this is no problem. Okay, so this is cosine to alpha to beta, and this is minus cosine to alpha minus 2 beta prime plus cosine 2 alpha prime minus 2 beta. Okay, so this is pretty straightforward, right? Okay, get it? Okay, no problem. Now, before we proceed, let's work with a specific example. So let's just say everything, this value, okay? And let's choose one setting. Let's choose one setting. 0, 22.5. Beta, 45. 16.5. Yeah? Okay. So let me just choose a setting. Why do I choose this setting? Because this will just make my evaluation easier. That's all. Okay, so 2 times that is 0. 2 times that is minus 45. So this is cosine minus 45. And 2 times that is 0. Minus 2 times that is 137. Thank you. Okay. And this is minus. Sorry?
135.
Okay. Okay, thank you. 35. I'm counting on you. So so this is 90. 90 minus 45, right? So this is 45. And this is, see, this is our 045. So that's why we choose this number, because it is easy. We can just write 1 over square root of 2, right?
Minus 45.
This is minus 90, and this is minus 135.
Why is minus
so
90? It's 90 minus 45, right? 90 minus 135.
90
Minus 135.
minus 135.
It's
Okay.
Minus 45.
Minus 1. Okay. Good. Thank you. So this guy is that. Okay. And this guy is
Minus 1.
this. And this is this. And this is also this. Okay, good. Everybody happy? Okay. And so this is plus, 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 plus. Everybody plus. So 4 of that is 2, 2. Okay, great. So this is what we calculate according to quantum mechanics. Okay? The quantum mechanics give us, just this. The quantum mechanics give us this. And we use this formula for this. Okay? This is a general measurements. This is like a general statement. And we apply this to quantum mechanical result, and that give us this. Great. So let me just write, this is quantum mechanics. Okay, now we erase this. Now we'll see the magic, which is the essence of the build test. Now, so this is quantum mechanics. This is, now we're gonna do hidden variable. Actually, we're gonna do local, real, hidden variable. Okay, because hidden variable just, actually, I think hidden variable represent real, because once the C is given, everything is predetermined. Okay, so really hidden variable represent real. So you just put local real, right? Local in front of it as an adjective. Okay, local hidden variable theory. So this thing means real. I know that there could be a possibility of non-local hidden variable theory. Okay, it's just not classical mechanics. Okay, and it is also not not quantum mechanics, but nevertheless, nobody forbidden you to build a non-local hidden variable theory. Actually, as a matter of fact, David Bohm, B-O-H-M, he has built such a theory called the pilot wave theory. Not the pilot wave theory. It's just the Bohm theory. Okay. Actually, the Bohr's pilot wave theory is sort of in the same spirit as Bohm's theory. So they are both non-local hidden variable theories. Anyway, so I'll come back to this. So this is hidden variable. This is hidden variable. Now we're gonna now construct some inequalities. Okay, we're gonna first take a absolute value of this guy. Yeah? Okay. Now the absolute value of this guy is if we take the absolute value of this, which is like in 1 under the same hidden variable, right? Sorry. Okay. So this is like the ensemble average. Okay. So this is equation 1. This is going to be smaller. Okay. Why? Because as we change the seed, right? This value basically just fluctuates like a random variable. Okay, so it is controlled by the seed, sort of like this. Okay, so the absolute value of the average of a random variable is smaller than the average of the absolute value of the random variable. Why? Because this is always positive. Right? You have a lot of positive values and you sum them together. While here you could have positive and negative. right? So it is not hard to see that this is gonna be less than this. Okay. So that's our equation 1. All right, now equation 2. Okay. Now let's take a look at this. Absolute value of this random variable is composed of these 4 quantities. And they are basically joint measurements, right? Measurement here for particle 1, measurement here for particle 2. Okay, so we have this. Let me write it here. Need bigger space. Okay, now it comes to remember we said that if it's local, then the result of measurement here does not affect the result of measurement here. So they can be factorized. Okay? So essentially this is equal to, okay, sorry, I need to give you the notation here. Ah, damn. So annoying. What? Yeah. What are you talking about?
I mean, we can set the result and we can show, just our result.
Yeah.
Is valid. That's all.
I don't see what you're saying.
I mean,
I have not finished. Okay, I have not finished. I have already given you the quantum mechanical result, but I have not given you the hidden variable result. So we don't know as of this point, we don't know if the hidden variable is going to give a different result from quantum mechanics. We don't know. Yeah? All right. But let me just continue with this very tedious notation per Musfa's request. Okay. All right. So what I'm trying to say here is the expectation value here is the same as the product of the individual measurement, right? Here, the measurement on the right give you alpha, give you some expectation value, and that has nothing to do with the measurement here. So the expectation value of both are independent of each other. So the joint measurement should be just the product of this, right? This is just the basic classical probability theory. The independent events, you can factorize it, okay? So I hope you see where I'm going with this. Okay. What does this give us? We can factorize this, right? Okay. Let me just use a different color. Where is blue? Oh, okay. Here and here. So let me just factorize it. So you see this local thing, this local assumption allow us to factorize a lot of things. So just remember this is due to local, the local assumption. And the hidden variable is the real assumption. It's associated with the real assumption. And this is real. This is real assumption. And this is the local assumption. Okay. All right. So that gives us this. Plus. Yep. Hi. Now, as we could imagine, individually they could take -1, +1. They are just randomly fluctuate according to your seed, right? According to your hidden variables, random seed, right? So if we take the absolute value of this, then you can imagine that this is not gonna be smaller than the average, the expectation value of this term, the absolute value of this term plus the average value of this term. Yes. It's basically this smaller than this plus this. Yeah, duh, right? Okay, but I'm gonna write it out. Okay, so this is just that. Okay. But by the way, I don't know if you heard this. So this is our first, so we start from here. Okay, the reason we're trying to calculate this because we have this. Okay, and what this says is the average. The average, if you take the average, then it's basically a lot of these terms. Sorry, just imagine this is a random number, right? So since they are all random, -1, +1, whatever. Okay, yeah. So this is a random number, okay, and this is also a random number. Now, if you take the random number before you average it, you just take it and then you make it all positive, and you average it. That will give you a result larger than you average it and then you take the absolute value, because within this absolute value there could be +1 and -1, right? They can, yeah. So this is from a mathematical point of view, it's not hard to understand. Okay, just put in the average. You switch the order of averaging and taking absolute value, and I'll give you this result. This is pretty general mathematics. All right, so that we have that, and okay, and of course this is let me just continue it because I'm running out of space.
So originally, our study just our system would be -1 and 1.
Yeah, the expectation value is basically because the expectation value is the joint measurement, right? And your outcome, your individual outcome is either 1 or -1. So the expectation value is either 1 or -1. So sorry, not the expectation value. The individual outcome is either 1 plus 1 times 1 or 1 times -1 or -1 times -1, right? All right. So yeah, but here it does not depends on whether you use -1 or 1. It's just a pretty general argument. All right. So now we have now we have that guy. Okay, this is equal. Oh, sorry, this is smaller than this, right? Now, this here, this vector here, this is a random variable that oscillates between 1 and -1, right? So what if we just we can estimate its upper bound, and the upper bound is that they are all 1. Okay, let me just say you can factor that. This is smaller than if you factor it out, right? Of course. Yeah? Yep. Okay. Yep. All right, so this is no problem. Now this has an upper bound, right? This is an upper bound of 1. So this naturally is smaller than this. Okay? Yep. Agree? Yeah? Okay, now let's estimate what is the possible outcome of this? two numbers. The possible so if we have, okay, let me just write this down. Psi. Okay, let's see if we can verify this.
I think it's trivial, right?
Huh?
I'm not sure, but it's saying trivial.
Trivial?
Yeah, because if you have beta x and then beta prime, will either plus or minus, then you get one of the possible values.
Okay.
It's 0 or 2.
Okay.
Yes.
If you say so.
Yes.
Let me just use one example, okay? If I have 1 here, right? Because I told you this is only 1 minus 1. So if I have 1 here and I have minus 1 here, okay? So the maximum of this is 1, right? And the sign here is, we have the positive sign, we have the minus sign, right? And the minimum is minus 1. Yeah? We're just trying to verify if this equation is true using a simple example. So this will give us 0, right? And here we have also 0. So 0 equal to 0. Yes, they are equal. Okay? And yeah, maybe you're right. It is trivial because of this and that reason. And if you agree, then it's not hard to imagine that you can, if just with the sign flip here, is basically you just flip a sign here. So this is become a plus. Okay? So let me just write it really, really fast. Plus, because we have a sign flip here. So here we have a plus. Oh, sorry. I forgot. Okay, so these are absolute values. Okay. So minimum. Oh. Hey, I made a mistake. See, the minimum is +1 because I have an absolute value here, right? So this give me 2. Yeah? And what happened here? This is not 0. This is 1 minus minus 1. So this is also 2. Okay, so it was not 0. So again, 2 mistakes make it good. But anyway, here when we swap, when we change this to a positive sign, then it's basically minus this value, right? And since here we have all the absolute value, this doesn't change, but this it changes here. It flipped the sign here. Okay. All right. So what I'm trying to say is that this whole thing is equal to twice the maximum value of these numbers. These two random numbers. Get it? Yeah, because you sum them and then they'll just differ by this. Yeah?
This will be always less than 1.
Yeah. That's correct. And this maximum is, of course, this is 1. This is upper bound, right? The upper bound is 1. Upper bound is 1. So this is less than 2. Okay? And so you see, we have gone through all this trouble to estimate what this is. An average value of an individual measurement, right? So this is less than 2, right? Therefore, so we have our equation 1. Equation 1 tells us if we do the average and we take the absolute value, then it will be smaller than we take the absolute value first and then do the average. And now we know that each value in the average is upper bound by 2. So this is average is, of course, 2. Understand, guys? Each value in the average is less than 2. So the maximum possible average you can get is 2. Right? Get it? I hope. So this is number 2. Equation number 2. This is the scope. Here we prove the CHSH inequality. This is a general result for all local hidden variable theory. The absolute value of your measurement of that very strange parameter. Okay? You take that strange parameter, right? And you do an ensemble. So you do measurements and you average over all your experiments. And whatever that is, you take the absolute value. And the classical theory, the local hidden variable, the classical version of quantum mechanics, so quantum mechanics 2.0, tells you that this must be less than 2. Yeah, exactly. So here we have a sharp boundary at 2. A sharp boundary at 2. And there's no overlap. On the right side, we have the local hidden variable theory. On the left side, we have the quantum mechanics. They don't overlap. So this is like a smoking gun experiment.
Is there some alpha and beta?
No, there's no max of quantum mechanics.
So if we take a different angle, do we get...
or maybe let me say this way. If you have an entangled state, then the entangled state will give you a violation of the inequality. If you don't have an entangled state to work with, then you might, but you don't necessarily get a violation.
So there will be some alpha and beta such that it will be less than this, right?
Could.
Yeah.
Could.
So that's not a problem.
That's not a problem.
Okay.
Because the deal here is they are not one-to-one mapped. we're trying to find a local hidden variable alternative for quantum mechanics.
So we can say if the value is greater than 2, it is quantum mechanical, but we cannot always say if it's less than 2, it's quantum classical, because it can be quantum mechanical sometimes, right?
Right.
Yeah.
If it's smaller than 2,
Smaller than 2,
and
sometimes it's quantum mechanical or
He's
classical,
saying that there's no restriction for quantum
but
mechanics.
if it's greater than 2, means classically restricted by 2, but quantum mechanically it can be less than or greater than 2.
Right. So you just need to find.
Because this is only one.
You just need to
example.
find a parameter.
if it's classical, it should be smaller than 2.
Yes.
Right.
And
Whatever your
quantum
parameter,
mechanically,
whatever your parameter choice. Okay, so whatever your parameter choice, it will always give you smaller than 2. Okay, because here we did not use and we did not give any specific value for alpha and beta, right?
and some specific value, you get is lesser than 2. So it's quantum mechanics. That's right. Or maybe absolute value. I mean within that range.
Classically,
Like
it's always less than 2,
minus 2 and 2.
but quantum mechanically, it can be greater than or less than 2.
Right. So you choose the parameter such that the quantum mechanical prediction is greater than 2.
That 2
Okay.
to 2 is the specific case of 0, 22.2, 45, 67.
It's like you have 2 variables, minus 2 to 2. It's classical. If it's smaller than minus 2, yes, and it's larger than 2, so it's
Larger than 2, it's always quantum mechanical.
and it's smaller than minus 2. It's quantum mechanics too.
Yes. Quantum.
Yes.
You say
Yeah.
smaller than 2.
Means absolute value.
Okay.
Absolute value.
So guys, so this bond is for local hidden variable, all the result within this bound. But quantum mechanical, it could be everywhere. Okay? Depending on the state you use entangled state, you use product state, whatever. Okay? But what you want to do is you want to pick an experiment parameter so that the quantum mechanical prediction is here, outside of the local hidden variable bound. And then you can see if your experimental result give you this or this.
Yes.
That is how you tell if nature work according to your standard quantum mechanical or this 2.0 version quantum mechanics. Okay. And okay, and then we're running out of time. But I think this is clear, right? I hope this is really tedious math, but thankfully we have this, and it casts this Bell test into a very approachable, understandable form. So if you want to read it, that is greatly encouraged. All right, so now we understand what's going on, and we don't feel like this is weird. Now let's talk about how we actually implement it. Okay, this is our last lecture, so I'm sure you don't mind that I again go over time. Since this is our last one. Half hour, because I need to.
Half hour?
Yeah.
Really?
Half hour. You stay. You can play this game and you can win a bonus. Just stick around for another half hour. Oh, you can go and come back later in half hour. It's okay. Come on. You can go. I won't stop you. I'm just saying that explaining the optical implementation, which you will do next week.
So can
Yeah.
Can I join the same?
Can you join the same? Yeah, you can do this. No problem. We will have the Deutsch and the polarization both set up, and everybody go. So the bonus lab is in the quantum optics lab, and there is a Deutsch table and there's a polarization table. There's a Bell table and there's a Deutsch table. And you can, yeah, TA will be there to assist you. And you can do, I think it will be easier to do the Deutsch first and then the polarization, because there are actually a lot of lab you can do with the polarization. And the measurement power will take longer. So if you just knock off the Deutsch, then at least you know how it works. Oh, what was the numbering? 8? Anybody remember? What was my last board number? Gosh, I think it's 8. I think it's 8. All right. So how do we make entangled state optically? So if we want to do that experiment, right? That experiment will just plot out. If we want to do it with our optic setup, how do we do it? There are 2 ways you can generate entangled photons. Okay? When people say that you put 2 systems together and then you make it touch and then they entangled like magic, don't believe it. This is just nonsense. Okay? You don't just touch it. You need to do more things like collapse, like post-selection. You need to do that in order to make an entangled state. Okay? So how do we not do that to make an entangled state? How do we not do like a post-selection, that kind of stuff? Because that involves a lot of procedures and it's very complex. Can we do it can we generate this entangled state in one shot? Okay? There are 2 ways to do it. Let me first tell you the simple way. It's called type 2 SPDC. Yeah? So type 2 SPDC is, okay, let me just start with type 1. Type 1 is what we are familiar with, right? You have a pump, you generate a concentric cone, you generate concentric cones of photons, and SPDC, and your photons are basically the same. So the degenerate, of course, the degenerate one, they generate in energy. They have everything the same except that their momentum are opposite. The polarization are the same too. Okay. And since this SPDC process will, the phase matching can only be achieved through using both the birefringence property of your nonlinear crystal. So it is necessary that in this case, you will align your you will put this, you'll make your pump beam extraordinary polarized. Yeah, it is very hard to explain. But let me just write this: E-O plus O. Okay? That means the 2 output photons have their polarization along the ordinary. But the thing is, ordinary polarization is not just like one axis. And extraordinary is not also one axis. They have like certain relation with respect to the optical axis. So it's kind of hard to say it this way. But what I try to get to is that in type 1 SPDC, the generated photon will have polarization orthogonal to the input pump photon. Okay, that's the most important thing. Okay, and that's the result. And the reason is because you need to invoke both the extraordinary and ordinary index of refraction. Okay, so we have like a whole thing, a whole lecture about this previously. Okay, for type 2 SPDC, the input photon could have an arbitrary polarization. It doesn't matter. Okay, it doesn't need to align with. It can align with the ordinary. It can align with the extraordinary. It doesn't matter. Okay, and the output will be orthogonal to each other. Okay. Okay. Now type 1 will give you a concentric cone. Yeah. But type 2 will give you an offset cone. Sorry. Not like this. Okay. Why?
Because ordinary and extraordinary will be different angle.
Okay, that's a good explanation, but that's the real reason is when you generate the extraordinary cone. Okay, when the extraordinary cone. So we won't spend too much time on this because we already talked about this. But when you generate the extraordinary cone, okay, like this, right? And these two momentums, right? This is a different index of refraction from, so this momentum, this moment, photon with this momentum and photon with this momentum, they see different index of refraction, right? Because the angle between K and the optical axis are different. So therefore, when they go outside, you know, when they go outside, the you have, you know, NE1 to the air, and you have here NE2 to the air. So yeah. So anyway, what I try to say is it is the center. The center of it is offset from the pump. Sorry. Okay. So what I'm trying to say is the center of the extraordinary cone is offset from the pump axis because they see the propagation.
And E1 and E2, because it should be E1 and O, right?
Huh?
Why is an E1 and E2? Should be ordinary and extraordinary, right? So
No. I'm just talking about, right now I'm talking about
only
I'm talking about why there's an offset for extraordinary, because in type 1, right? In type 1, why there is no offset? Because both are ordinary. And the ordinary index of refraction does not change with your angle. But extraordinary does. So when your angle is different, it changes. Okay? And somehow this is not symmetric. It's not symmetric. So I would imagine if you have this, you know, they would change in the same way, but somehow this is not the case. I don't really understand why, to be honest with you.
Because it has different angles.
Well, it has the same angle. Like if we
means extraordinary has different angle.
No. If this is extraordinary, this is like in one process, and so this is, for example, this is pump, this is one generate, so signal, and this is idler, right? And in another case, this is signal and this is idler, right? So in two different events, if this just has the same amplitude in vertical direction, I imagine its counterpart will also have the same angle. And so I'm trying to say the uppermost part of this cone and the lowest part of this cone, I think they should be symmetric, but somehow,
because in a medium, if it's refracting to the right or left, it depends, right? So even though they're both in the same angle, if it's refracting to the right, both will tilt to the right. So it seems both are off axis, right?
Oh, right. You're right. Because say the optical, right, you're right. Thank you. So say this is the optical axis, right? And so although these two, K1 and K2, they are both although they have the same angle with respect to the KP. The momentum angle. The momentum angle. But because they have different angle, again, the momentum with respect to the optical axis angle are different, right? So this will experience a different index of refraction than this. Okay, so this will make it go down. So at least when it goes out, it will definitely go down, because here we have the Snell's law, right? So if this is different from here, this is different from here, definitely. If not inside, it will do this outside.
Inside also, because extraordinary travel speed less than that of light, right?
All right. Yeah. Because the position. Anyway. So here, the upper part and the lower part of the cone will not be symmetric along P, even though initially you have them in the same. Okay. Now, what I tried. So this is offset. So this causes this offset.
We can say like it will refract at the same angle, but to same direction.
You will reflect the same.
Means, for example, so if I'm saying we have this angle as theta, and our shift, this is phi, we have that shift phi here. So it refracts phi to here and phi to here.
Okay.
In the same direction.
So we have a cone like this instead of this.
Okay.
That's
Thank you.
what I'm thinking.
Oh, okay, that's great. Thank you. All right. So he's saying that even though they are generate initially like this, but the propagation
and refraction.
The propagation will cause the bending of the ray, so that this goes like this and this goes like this. That cause the econ to get shifted. The center of the econ to get shifted. And here, why it doesn't matter? Because both beams are O, and O and here both beams are O, and I'm still talking about from the same cone, okay? But here and yes, they have different angle with the optical axis, but that doesn't matter because they are all polarized. So their polarization is perpendicular to the optical axis. So their index of refraction does not change according to the angle with the optical axis. It is really because of this E that we have an offset, okay? And since we have an offset with E to compensate for the momentum, because the transverse momentum needs to cancel, right? Because here we have only the longitudinal momentum from the P. So that if this goes up, and then another one that is opposite direction needs to go down. That's the ordinary, okay? So this E dictate this shift, and O just shift in opposite with that. Okay, but that is due to this momentum conservation requirement. All right. So anyway, so if we place this right, we could make this O to be horizontally priced, and make this E, make this E to be horizontally polarized, and this O to be vertically polarized, right?
You mean at the creation, or after that we use lambda?
No. Just by how you position the optical axis with respect to the table. Okay, because the optical axis and the pump, they span a plane, right? So if you put this plane parallel to the table, then this is the then polarization. The output polarization with this is V is the ordinary, and this will be the extraordinary. Okay. All right. So this is possible, and so you see you generate every time you generate. So let me just make this larger. Right, this is the pump, okay? So every time you generate a particle here, a photon here, you'll have the opposite momentum. So this is the correlated pair, okay? So this is your counterpart. And if you generate it here, for example, then this is your counterpart. So always the momentum conservation dictate that the transverse momentum needs to cancel. Okay. Now, so this is photon 1. This is photon 2. This is photon 1. This is photon 2. Right? Okay. So in this pair, okay, let's take a look at this. In this case, we have this is V. This is H. So we have the first particle as V and the second particle as H. Right? So this is our first pair. And let me just use 3 and 4. 3 and 4. Okay? Yeah? So this is the first pair I generate. The second pair I generate has, again, it is 3. It is 4. Right? Okay. How about this? This is a bad drawing. How about this? 5 and 6. So these are all product states.
Why? Yeah. Yes.
Okay, so these are all product states. Yeah? How about 5 and 6? 5 could be from this cone, or it could be from that cone. So 5 is in the superposition, right? H or V is in the superposition. Now, if this is H, then the other one must be V because they are orthogonal, right? So this must be V, right? It must be from here. And this, when it is at this position, it could be also in a superposition H or V. So this is H. Sorry, this is 5. Okay? So this gives us the entangled state. Yeah? Okay. So this is the first way to generate entangled state in one shot. But you need to put a pinhole here because only this regime, you have this entangled property. Otherwise, you have the product states. Okay? So this is type 2. And there's this. So this is type 1 with single crystal, and this is type 2 with single crystal. Okay? Single crystal. And this is single crystal. Okay? The other way is type 1 SPDC, but double crystal. Okay? And this will give us so a 45-degree input will give us E and O. Yeah? So how does this work? So imagine you have a crystal that looks like this. Okay? And here's your pump. Right? And your optical axis is arranged so that it is making, it spans a plane with this guy, with the pump. It spans a plane and the plane is in the horizontal. Yeah? Okay. For a single crystal, how will this work? We say that for single crystal type 1 SPDC, the polarization here needs to be extraordinary, right? So what does extraordinary mean? Extraordinary, because I'm out of time, so I'm going to just read it. So ordinary polarization is polarization that is perpendicular to the optical axis. Okay, so anything that is perpendicular to the optical axis, that is ordinary polarization. Okay, and for field with ordinary polarization, it will experience stronger interaction with the crystal molecules, and that will result in the lower light speed inside the material. Okay, therefore, lower light speed means the ordinary index of refraction is higher. Now, what is extraordinary polarization? Extraordinary polarization is the polarization that is partially or fully aligned with the optical axis. Okay, so if you have a polarization that is like this, that is extraordinary. Okay, if you have a polarization that is like this, that is extraordinary. Now, if you have a polarization that is this, that is extraordinary. If you have a polarization that is this, that is ordinary. See, so there are a lot of extraordinary options. So once you don't know what is extraordinary and ordinary unless you have first defined your input momentum, and you know the optical axis of which is the crystal axis of this thing. Once you know that, you can use this plane to decide what is ordinary and what is extraordinary. Okay, and so if we have a wave that is propagating along the optical axis, then of course it's gonna be since the polarization of the wave is orthogonal to its propagation. So if the propagation is along the optical axis, then it is automatically ordinary, right? But this is like a very rare case because out of all these directions, there's only one direction. So most of the time, 99% of the time, we have an angle with the with the optical axis. Okay, so it's more like this. This is like the typical scenario. And if we have an angle, then we have two scenarios for our polarization. If we have the polarization that is perpendicular to the plane that we span, that is the ordinary polarization. And if we have a polarization that is in plane or partially in plane, have a projection on this plane, then that is extraordinary. Okay, so having clarified the terminology, I now want to say that we put if we put this like this, that is extraordinary polarization, and type 1 will give us this ordinary, right? Now, what if I put two of them together? What if I put two of them side by side? Okay. And I make okay. I hope you understand my drawing. So what if I just flip this thing? I just get a sand crystal and I just flip it so that the optics axis is like this. Okay. What would be the extraordinary in this case? So this is the output. What would be the extraordinary here? You'll be this, right? In plane is one of the options. Okay. If I put this in plane, then this will come out will be this, right? Okay, so this is vertical, this is horizontal, right? Now, this is good, yes? How about if I put this in? I put an ordinary in to start with. Here, the pump will be ordinary, so it won't do anything because the type 1 HBT requires it to be an extraordinary. Okay, So you won't do anything here. Okay, you won't do anything until here. Then you will do something, right? What if I input something like this? Then you will do something here. It will break into 2 photons, someplace. But when you enter here, no chance. Okay? What if our input is in a superposition? So it's 45 degrees. And since we're talking about single photon, because SPDC is a single photon process, right? Single pump photon break into 2 output photons, right? So what if this is 45? What does 45 mean? 45 means the photon is in a superposition of H and V. Yeah? So what that means is this single photon has the opportunity to break here in the first crystal, or it will have the opportunity to break in the second crystal. Okay? If it break in the first crystal, the light you emit, okay? The 2 light you emit is this. Right? But if it break in the second crystal, the 2 light that you emit is this. Okay? And since this is in the superposition of this and that, this breaking here or here, that also is in the superposition. Okay, so we can engineer using this double type 1 SPDC crystal to engineer an entangled state like this, just as we discussed. Okay. Now there are a lot of more. So this is the basic of the optical implementation. Like this is the core, and I want to talk about this a little bit because this is like the common picture that you see in quantum optics. You have like 2 rings, and at the intersection you have the entangled state. But we can make the same entangled state. Although, sorry, this type of entangled state is different from this because this, you see, this is SAN, HH, VV, and this is HV, VH. Okay, so these are 2 different category of Bell states. Okay, but nevertheless, this is a Bell state. This is an entangled state, so it can be used for the Bell test. Okay, now what I want to say is that there are a lot of technical complications into this that can affect the relative, because you're essentially having 2 cones, right? And you overlap them. So the cone radius matter, okay? And the cone radius is determined by the angle between the optical axis and your pump, right? So if this angle and this angle are not the same, right? You don't have entanglement. The ring are like, they are like this. They are not overlapping. So HH ring and the VV ring, they are not overlapping. Only when they are overlapping, this is a superposition. Okay?
Do we take the whole ring, or after the ring we just take a position in the ring and pass that into the second crystal?
No, they are back to back. You take the whole ring and the whole ring.
Oh.
But the point, no, don't get mistaken. Don't misunderstand. It is not, if this becomes a ring, yes, then that ring doesn't, I mean, it's already break. Okay, it can only break once.
Yes.
Okay, so there's nothing else that will happen here if it breaks here. Okay, versus if it breaks here. Okay, so this is like 2 paths of of a beam splitter. You can either go this path or go this path.
At the output, we will have 2 rings. Right?
You have 2 rings, and you need to overlap them. You need to adjust the angle to overlap them, so that you cannot distinguish which one.
Okay.
If the pump
So in the optical setup, do we combine the
how about this? Here you will have like the mole function, okay? Here you have the mole function, and the mole function needs to be fully overlap, so that they can become a superposition. If they are not fully overlapped, then they become distinguishable. This is the same as the interferometer example that we talk about, right? So just know that this is one complication. The second is the detector. Okay, this is generate first. If this is the ring, so if you do if you do VV, this is generate first, and this is generate later, right? So temporarily there is a time delay. Okay, so that can in principle distinguish these two things. Okay, and if the time delay is really small, it can still be due to the optical path difference, like small optical path difference. You can still have a phase offset to this. Okay, so I'm just trying to say that when we do it this way, there is a lot of technical imperfection that need to be taken into account when we analyze our data and try to see if it breaks the bound or okay, because what we're doing with the Bayes test is a delicate issue, and every systematic error matters. When we do it with this, of course, there's less complication because like this entanglement is like generate one shot. You don't need to do anything; it's automatically aligned. Okay. The downside is that you have only a very small portion of photons to work with. Okay, and so the alignment needs to be perfect. If you have a little bit of this and that will just bring down your result a lot. If you use a mixed state or a product state to do your Bayes test, you will be probably within the bound, within the local hidden variable bound. Okay, so this has its pros and cons, and this has its pros and cons. And the nice thing about this setup is, although this requires a lot of alignment, but you can see how you can control the relative phase. Like in a sense, you can control the relative phase and the mole function. And you can see how does the entangled state is constructed. How do you successfully construct an entangled state, and how to spoil it. Yeah, so you can.
We need a really high power pump, right? Because at the small angle we need to.
Yeah. Correct. Like this is yeah. All right. So anyway, that's
so that. One are we doing in the lab?
Here, we're doing this. So this is what we do in the lab, and so this is like the very basic overview of the optical implementation. If you're interested, I encourage you to read this menu online. Okay, it has a lot of good stuff. Okay, so we will close here, and thank you very much for the entire semester being out with me, because I didn't expect that every lecture is like 3 hours, or and it gets worse these days, 4 hours. I couldn't help it, but it is what it is, and I just hope that you have a good time and you learn something. All right.
Hong-Mandel is not there, right?
No. Yeah, we don't have time to do that. So very sorry, but we have done the best we can. Maybe we will see if it will work next semester. All right. So quiz. So we do a quick quiz. So this is our 2 problems. Pretty simple. Okay, let's get moving. Okay, come on, Phoenix. You can think later. You can think when you talk, when you start. If you have no idea what I'm talking about, that's perfectly okay. Just try to stand at the opposite side as him.
I'm not very sure.
What do you mean by reject?
Yes. I mean, but
So real and local are the two properties, two features
No,
that we talk about, right?
What do you mean by reject? It's like
Reject
Because-
means
because-
S is less than
you mean whether
less
you
than
mean
or equal to
restriction?
2.
I mean,
Mhm.
You mean it accepts this condition or
yes,
it violates this
yes,
condition?
But, yes, what do you mean?
or reject means distinguish the prediction between this. Have a setup
Means
that
You
that
say
that
it
fully
will-
distinguish.
it will be greater than 2?
No, reject means
Oh,
compare it to quantum mechanics.
I think it's like, maybe if we reverse the question, like, can the test restrict or quantum mechanics?
Or distinct.
That's why I'm
Okay, maybe not the word reject. Maybe distinguish all real theory from standard quantum mechanics. Okay. QN. Okay. And distinguish. So I hope this language is better now. Distinguish all local theories.
Yes.
So I
So
should
now it's better, right? I mean, we do better test.
from. Okay, you can start debate. Are you voting for yes?
Yes.
And he is voting for no. Great. Say you are wrong. Start. We don't have much time. I need to go.
Okay, you're wrong. Because
My reason is like all quantum mechanical theories will not violate this, right? So how can
I mean,
Oh, don't tell me it's raining.
reason is from the local system, right?
yes, but
Because
even some quantum mechanical theories are in
Debate.
this range.
Let me check if it's raining.
can this one, I mean, this one, can distinct all the real theory from the standard one. So, I mean, if you have the range, so you mean if there's a local hidden variable, right? So this one should be, I mean, this one is the classical constraint, and it should be follow this, I mean, this one, what you wrote
Yeah,
right
but
here.
even
but
in
if-
this, quantum mechanics theory can give results in this range, right?
Oh, okay, I see.
You
Okay.
understand?
Yeah,
You
got
have
it.
this line.
Got it. Okay, yeah.
This is classical.
Okay. Just
This is quantum mechanical.
okay, yeah, you're right.
So I don't know how to distinguish
yes,
between these two.
okay. Just like there's a way to distinguish, but stay in between we cannot. Okay.
Yes,
Okay.
even if it give
Okay,
value in
got
this,
it,
right?
got it.
Okay. Are we good?
Yeah.
All right. Cool. All right. Switch. Oh yeah, you switched. You sure?
Yes.
Do we need a second round?
No.
All right. You're right. Congratulations. All right. Second question.
Same answer.
Second question. Okay. Choose your side
I stand with
And-
the same answer because
and-
of the same
and-
reason.
Yes.
and debate
Because
again.
I don't have any other reason.
Okay. Start. Start with you're wrong,
No.
and you will say you're wrong too,
You're wrong
and you say you're wrong too.
because of the same reason I gave.
Yeah.
Yes,
I mean.
we cannot distinguish between them.
Yes.
If it's outside the range quantum mechanics,
Yes.
then we can distinguish. But there are some particular cases it's in the range, so we cannot distinguish between which is which.
Are you sure? I'm not so
Yes.
sure your argument is correct, and I'm not bullshitting you. I'm not so sure your argument is correct. Maybe just spend 1 minute debate with each other.
Yeah, I think he is right.
No, that's not your line. Your line is you're wrong. He's wrong. I'm right. Even though we are on the same side, I'm right. He's wrong. That's the spirit. Are we done?
Yes.
No debate?
No.
Come on. What's the fun?
We had the debate.
All right. Okay, you're right. Congratulations. Okay, but this is probably not the reason you think.
Because actually, I think.
Remember this thing I draw?
Yes.
Local, non-local, real, not real. Okay. Field test is designed for test for theory in this category only.
Okay.
So if you talk about all real, that's like this, this and this. Field test cannot cover this. Okay. And if you talk about all local, that's this and this. And field test cannot cover this either. So the validity range of its analysis is only limited to local and real. Any other combinations are not in its capacity, are not within the capacity of the field test. Okay, it's not really the range stuff. It's just how this thing is designed. Okay, cool. So for example, the de Broglie theory, the Bone theory, the David Bone theory, that is non-local real, and you cannot use field test to tell if this is different from quantum mechanics.